Yeah, so the title of this talk is From Healthcare.hospital Import Data Science. And a short introduction, where are we from? We're from Amsterdam, the both of us. We work at the Netherlands Cancer Institute, which was founded in 1913 on the left. It was the first hospital on the famous canals. And they started out with a medical staff of just a few guys, still smoking cigarettes and cigars back then. And nowadays we have a very modern hospital and also a combined research institute. So the hospital is called the Antonie van Leeuwenhoek and the research institute is called the Netherlands Cancer Institute. So it's a dedicated hospital / research institute only for oncology. All right. And we are going to tell you about a data science project we just recently started in our hospital and more specifically in the Department of Radiotherapy. Let me first walk you through the people who are, let's say, involved in this data science project. So on the left, we have, let's say, we call it the clinic. It's comprised of the medical doctors, the nurses, medical technologists, and medical physicists. On the right, we have research and development. We have, let's say, principal investigators, postdocs, PhDs, students, and software developers. And while I was going through my slides, I found that I forgot one very important group of people, which is the patient group, who probably they don't like it, but they provide us with the data we hope to do something useful with. Okay, so who are we? Both Pavlos and I are physicists. We did our PhD in, Pavlos did his PhD in Monte Carlo simulations of small dosimetry fields. And I have a background in theoretical high energy physics, but we both had, let's say, we both like hospitals, I don't know why. And we switched to medical physics, and once we were in hospital, we switched to data science. We're not data scientists, as everyone is nowadays, but we're still physicists, but we do like data. And I think our, let's say, our overall ambition is to extract meaning from all the data we have, let's say all the clinical data we have, and to assist with this, to assist the decision makers in their clinical decision making. All right. Now, like I said, we are from the Department of Radiotherapy. I'm not sure if you're all familiar with what radiotherapy is. It's the use of ionizing radiation to kill a tumor cell, basically. And let me walk you through the radiotherapy chain. So this is what the, let's say, the workflow in a radiotherapy department looks like. In the upper right for you guys is the consultation, so that's where the patient meets for the first time with the doctor. Then this patient goes through the process of diagnosis, and I also highlighted what kind of data we gather from these several steps. So at consultation, let's say it's medical data, lab results, or written data, oral data, whatever. Diagnosis, we enter into the imaging phase, so you get a CT scan or an MRI scan or a PET-CT or whatnot, and you have lab results, etc., etc. After diagnosis, you go to the so-called tumor and organ delineation, where, let's say, there's more medical imaging and processes performed on these medical images. From medical imaging, you go to the treatment planning, where we do simulations of what kind of treatment this patient should get. Once the simulation is done, you go to the actual treatment, and then you go to the outcome of the treatment. And along these steps, there's more data gathered, more lab results, medical imaging data, etc., etc., etc. All right. Well, our ambition is to assist the decision makers in all these steps with making more informed decisions to better the treatment for the patient, of course. So let me walk you through the several decisions which are made in every single step of this clinical workflow. Now, let's say at the first step, at the consultation, it's a very basic decision which needs to be made by the doctor. Is there a problem, right? Then the patient goes to diagnosis, and the doctor decides, well, is there a tumor? Next step in the tumor and organ delineation, so if there is a tumor, where is this tumor? And the technician then steps in and he tries to find out where are the organs relative to the tumor. Once these decisions are made, you pass on to treatment planning, and then the physicist steps in and he goes on to decide how should we treat this patient given the knowledge of where the tumor and organs are, etc., etc. Well, then you go to the treatment itself, and then another technician steps in, he performs the actual treatment, and he or she decides, well, has the patient changed, etc., etc., etc. And after the actual treatment, the doctor decides, okay, was this treatment effective? Do we need to change anything? All right. So this seems to be, there's a lot of room to make data-driven decisions in this whole clinical workflow. So you would expect there's a huge, let's say, at least enthusiasm for AI or machine learning methods in medical healthcare. But to our understanding, there's little to no practical implementation of data-driven methods. But there is a lot of research, and I want to try to tell you why there's still, let's say, incongruence between these two groups who all share the same goal to improve treatment for patients with cancer. So in the clinic, we don't have many data-savvy people. Workflows often change, so that's hard for you for your, let's say, for structured data gathering. And people don't trust much in models. They're still, okay, we've been doing this all our lives and it's been working, so why should we change anything? Why should you tell me that I should do something better, you physicist? In research, we have a lot of data-driven people. Of course, we like data, we physicists, but there's a different incentive in research. You want to publish or perish, right? And physicists or researchers, they tend to like original ideas, and they don't care that much about implementation. So if it's interesting enough for a researcher, he will pursue it, but he will not care about the actual implementation. So there's sort of a discrepancy between these two groups. And more so, there are also restrictions on the data we actually gather. So I phrased these as questions, and you might think about them yourself now. So for example, is in-house developed software a medical device? Can I share my code with other hospitals or companies? Who is allowed to work with patient data, and can data scientists actually work with medical data? Now, these questions are not answered, but they're going to be answered. This is, for example, the General Data Protection Regulation. This is laid down by the European Union, to, let's say, to formulate a good answer to all these questions in medical data, because there are privacy laws, et cetera, et cetera. All right, just a small side step. What is the data I'm actually talking about? I'm basically talking about medical imaging data. And in the 1980s, there was a whole lot of mess of different imaging standards, and they came up with a format, and it's called DICOM. It's called the Digital Imaging and Communications in Medicine, and it's the international standard of medical imaging data, and it includes CT images, MR images, et cetera, et cetera. There's a nice Python library we use called PyDICOM to handle all these objects. But the thing is, to work with the data is very difficult to query this whole assembly of data, because it's a graph-based data. So it's a little bit more cumbersome. All right, what's the amount of data we're talking about? Well, at the NKI, the Netherlands Cancer Institute, we treat on average 5,000 patients annually among all tumor sites. So I mean, different tumor locations, head and neck, breast, lung, et cetera, et cetera. On average, 250 patients per site. So that would, you would say that's a lot of data, and it is. But the problem is, there's a big variation in the image acquisition and imaging modality in patient data. So patients might start with a CT scan, but then the doctor decides, well, he or she needs an MR scan, or I should complement it with a PET CT. And it differs per patient, and it might also differ per doctor what he or she thinks is more relevant for this patient. So it's difficult to gather as a nice formalized data set. Now, we want to assist the decision makers in their clinical decision process. So where should we start? Ideally, you would start with a consultation and predict the outcome. But we're missing a lot of data to do this. We don't have reliable outcome data, for example. So what we did, we went backwards to this clinical workflow and decided, well, where could we, as physicists/data scientists, have the biggest impact? Now, in treatment, there's little room to do anything. Okay, so we go back one step, treatment planning. Still not really a lot of room to make improvements. You come to tumor and organ delineation, and it's highlighted in green, so this is what we're going to talk about, of course. We did not focus on diagnosis because that's also the interdepartmental stuff. You need to work with radiology and radiotherapy, and you have to deal with a lot more people, so it's also more cumbersome. So we decided to focus our attention on tumor and organ delineation. Pavlos will tell you all about the details of this project. And this is also very general, but we decided to stick to head and neck cancer specifically. It only accounts for, let's say, 5% of all cancer cases worldwide, but the outcome is poor, so there's a lot of room for improvement. As you all know, head and neck cancer is caused by the fun things in life: smoking, drinking, oral sex. Sorry, cannot do anything about it. And we decided to focus our attention on the so-called delineation of the salivary glands. Because in a head and neck radiotherapy treatment, they also receive radiation dose. And if you receive too much dose, you will get very serious side effects later on. They are called, for example, xerostomia and dysphagia, which means a dry your salivary glands won't work anymore, you will get difficulty in swallowing, which will seriously hinder your quality of life. All right, so we're going to talk about the organ delineation. It's also called contouring, and what this means in practice is that the clinician, he annotates CT medical images every day to specify the organ shape and location. It's called an organ contour. Now, this is a very difficult, time-consuming, and still very manual process, often biased by personal opinion. People might differ about what the correct contour should be. And it is not always clear if a contour needs corrections or if it's okay to proceed for treatment. All right, I hope I set the general stage for what we want to do, what we intend to do, and now my colleague Pavlos will tell you more about the specifics of our project.
Hello. Yeah, so picking off where Patrick finished. So yeah, so we focus on the contouring of organ delineations, and this, for example, would be a CT image of a patient before he goes to radiation treatment, and most of the contours have been contoured by Somali. Still, it's a very manual process, even though there's a lot of software offering auto-contouring possibilities. Our main hypothesis, though, here is the following, that a body structure should, on average, respect some morphological characteristics, and that's what we're tapping in. So whatever somebody did now, it's probably going to be very similar to what happened in the past. And machine learning and image contouring is not a new thing. It's a big thing in research world. There's a lot of algorithms that are focused mostly on the auto-contouring part. This would mean the algorithm predicts where the organ is and how does it look like. This is a competitive to the expert approach, basically meaning that in a few years from now, the expert's going to be out of job, maybe. Or a more collaborative approach to the expert is an anomaly detection system, which we are focusing mostly on this. And this because the algorithm then, in this case, we just want him to flag a case that was very anomalous based on previous historical data. So we thought that this would be a good way to convince also clinicians to be on our side, since it's not very competitive to their work to begin with. And before I get into more the details of this specific problem, in general, what is an anomaly? And this is an ill-defined concept regardless of the industry. We don't really know what we are talking about anomaly here. In this case, we're actually talking about medical error. That's what we want to catch. And however, some things to keep in mind, if you have some data points here and I ask you what were the anomalies, probably these 4 points would be outliers, but in a global context, this might not be true. So this is things to keep in mind, especially when you have a large population of patient data. And the other thing is context matters. Maybe you've seen this picture. Obviously, the red fish is the anomaly, but what was the question? Was it the question really if the fish is going against the flow? So context matters on the problems that you said to solve. So if we cannot define well what is an anomaly, then what is a contour anomaly, as Patrick explained a little bit about the delineations, and this is the case of a parotid gland that Patrick already gave you some insight of what it is. And this is something that even experts cannot really tell you, and that's important because we're not going to be able to label our data if we don't know that. Also, anomalies may be different in the future, so even if they do tell you, that doesn't mean that the same anomaly is going to occur again. However, we are saying that some shape characteristics should be respected. And this is actually the fact of an anomaly, what I'm showing here, because I don't know if you can see it there, but there is a little bit of a different contrast. That's an artery that's going through the gland, and the technologists decided to contour that out. So this is not part of the gland, I'm going to put it out. But this actually was wrong, because you need to include the arteries, and this was a contrast agent that was giving this difference. And if you think about it, then it's interesting because then you can do some feature engineering and say, okay, if they do that, then I can maybe define an index which will be, let's say, concavity index. So whenever they try to do something that's concavity index, my algorithm is going to pick it up. And in the same manner, you can build more of these features, such as symmetry of the shape, perimeter over area, simple stuff, things that we can explain easily also in the clinic. And there's a nice library in Python that was, I think, originally built for topological problems. That's called Shapely. if you have similar data, I suggest that you have a look on this. So this was a good starting point that we can easily extract these features. The other thing that we, so going to the modeling now part, one of the most common anomaly detector machine learning algorithms that are around, and they are in the scikit-learn actually library, is the isolation forest, which is an unsupervised learning technique. And in a nutshell, it's a decision tree, basically a random forest approach, in which case, with a twist though, the twist here is that basically when you're trying to do a split on your feature space on a feature, you do a random split uniformly between the min and maximum value, and then you continue doing that until all your samples are completely isolated. And the idea is very simple, that if you had very difficulties isolating a point, like in the case of the graph on the left, that probably indicates that the point is not really an anomaly. While if you can easily separate it and isolate it, so that means in the tree that it was actually shorter, the depth of the tree that you have to go until you isolate that point, that is an indication it might be an outlier. But again, we do need labels, as in any data science project, and we do not have label data. Most of the things in the hospital, you do not have label data. So what can we do about that? Two approaches. The one would be either you generate then anomalies, you can use some type of perturbation of the features that you have, but this might not be realistic enough. You might use distributions that they might not be accurate. We have explored this by using some monotonically decreasing functions with the assumption that an anomaly is probably going to be less likely to be a huge anomaly than a small anomaly. The other approach would be to have a domain expert, the clinician, that is going to label for us. This is also very difficult because labor intensive. They don't have that much time to do that for you. And then secondly, also, they don't know what an anomaly is, going back to that original question. So they're going to ask you, okay, how am I going to do that? And then a third one, they're also going to be biased. So they're going to basically create the anomalies that they think. But in reality, this would have been something better. So this is another approach that you can do. And from our experience trying to follow the best machine learning practice, but also be pragmatic, we found that it's not really, that we're not really talking about a data-driven approach. We're mostly talking about data-driven and expert-driven approach. So we start with training and testing a model just to get going. We run the model as it is if it's not perfect, but we let it run in the clinic and the expert checks, and then the expert sort of in this stage learns also what the model is doing. It gets a little bit excited, hopefully, and then he can also help you with labeling future anomalies. And then you do your feature engineering, and you go through another circle of this, where hopefully you're going to have now the expert generating anomalies for you, that you can do an even more serious validation test, and you do regularization, and then this can be an end, as you can imagine, can be an everlasting process, obviously. But this is a realistic way to tap into how to have labeled data. And the other area also, so even if you do that, and a clinician then is going to come and tell you, okay, your argument, let's say, says that this X data point was an anomaly, why? So, and it's very crucial because we're talking about patient data here, and you're basically saying that there's a medical problem. So these are heavy words to say in a hospital, so you have to explain yourself. And we don't know, but there are libraries out there that they can help you with that. And one of the libraries is called Skater that we're using. I know there's also another library that's doing something similar, which basically this is sort of a meta model on your prediction results, in which case they can highlight what exactly would be the, what were exactly the features that were really anomalous. And in this case, all the green bars are basically the features that were positive as anomalies, so green would be bad in this graph. And you can also see some range of values of what these features had. So for example, in the first two cases here, first two features were actually the lengths of the structures. And this is very useful information then for the clinic, because the clinic can actually get a better insight of what they were actually doing all these years. Even if you pass all these steps, you still have to build a pipeline in a hospital. And I wanted to spend a little bit of time on that, because It's not very trivial to do that in a hospital. Ideally, you would want to have a database of structured data, labeled data, let's say, and then you can split your data, do a train test, and run it on a server in a cloud, and then deploy it again on a server cloud similarly. The reality that we see looks more like this. We do not have really a database. There are some databases, but they're very vendor specific because hospitals work a lot with commercial software and they have their own databases, which you cannot tap into that. We do have other data warehouses where we have this DICOM image protocol, which at least we have the same format in our data that is saved. So we have to spend a lot of time, and luckily we had a very talented data engineer in our team that he can help us make these processes to extract this data. But even after this step, this data are nested data, graph-based data, meaning that I cannot really say, bring me a patient that had this CT. I cannot say that. I have to find on each patient, go to see, did he got a treatment, did he got a plan, did he get some imaging? If he gets some imaging, I have to go all the images. So this actually led us to a decision to build an RDF database. I'm not sure how many of you are using RDF database or no. They're not the most common, but and you have to use a Sparkle as a query language, which is a bit peculiar. But we had to do that first step. And then another problem is that when we're talking about servers in clinics, okay, you cannot put anything in the cloud. That's out of the option because these are sensitive data. You can't even use most of the servers that are in the clinic because these are dedicated for the clinic. So then they would ask you, are you doing research or clinic? If you're doing research, there's a cluster, but this is the problem now with data science. Data science sort of like has one leg on a different boat, let's say. Like, so we're trying to balance between these two things. So me, for example, technically I'm not allowed to see a lot of the patient data. So this causes a lot of problems. Our approach to this was, from that Sparkle queries, we created a SQL database that would be fast, because Sparkle is also slow, for our data, for our projects. Then we have modules to create the labels, which based on the process that I mentioned before. And with the servers, we still have ongoing discussions with hospital to try to have a dedicated server for data science projects. So all these that might be trivial in other cases, in our case, we have to fight for them. Yeah, in the previous step, another thing, the previous speaker also mentioned that how important visualization and analytics in your models are, and we also had the same experience. Clinicians are not gonna like probably running something on a command line, or they wanna see something nice. It gives sort of a credibility to what you're doing, even though this is not proven, but it's nice to see things in a nice format, and that's what they want to see at the end. So we put a lot of effort also to have like nice dashboards for them from the prediction database, so they can, and this also was good because the clinicians, you really want them to bring them in the same team with you, to feel that they are building something with you, so you're not competing with them. And in that case, for example, in this case, it's like a time series of the anomalies that were picked, and the red would show what, if it was anomaly, green would be not anomaly, and if you click it, it will give you also some feature importance metrics. So simple things like that they can help us, help the team us to understand better how the model behaves, but also the clinician gets a little bit more data, excited with the data. Yeah, so at the end, I wanted also to spend a little bit of time now to some of the results without really going through accuracy metrics, just to have some eye candies here of cases that we picked up that were very interesting in my case. So all these are anomalies. This is all from our models, and the models now are running in the clinic in parallel to the clinical workflow. So on the left, we see basically one slice of square shape. That's an error. There was a reason why that happened, so there was no compromise in the treatments, I should say. But this error, what I found interesting is that if you look on the bottom, the feature importance, indeed it gives you that, okay, there was a whole bunch of features here that were kind of exploded. It's very clear that this was an anomaly. On the second case, it was not an error, And this is, again, the case of a gland that you can see goes like really far up. And then when we went to the expert to ask him what's happening in this case, he actually told us, okay, this is not really the gland. This is sort of a duct that goes from the gland in the mouth. And we don't really know if this is part of our structure or not. Some people do this. Some people don't do this. So that's very interesting for me, because that means that basically my problem was not anomaly detection. It was basically consensus agreement. Like, is the team doing reproducibly what we think they're doing? And the other interesting thing is that the feature explanation also sort of had a borderline opinion. Like, some features are green, some features are red. A third category of anomalies are cases now that the shape was really anomalous, so it was clear there was an anomaly, but another factor that we didn't think of was that people that have head and neck cancers, they often go through surgeries, so they might have some malformation in the shape of their body contour, or they might have dysphagia, which means basically they cannot eat well, so they might get thinner. So the anatomy changed through their treatment, and this resulted in an anomalous shape, but it was not really an error. It was actually how the patient's body was changing. So this actually could be used also to see how patient's body was changing. So some final remarks and maybe some questions that raise to this process about building a data science pipeline in the clinic. First of all, the anomaly detector, I think it's a very exciting area of machine learning for hospitals. That's basically in hospitals what most people do. They're trying to find anomalies. And it can be used in many cases, I believe, like lab results, quality assurance checks, emergency room. But as Patrick said, in the hospitals, we don't really have data science yet. This is the reality. We do have a lot of data. But some of the reasons why data science is challenging is that we do not have yet data science infrastructure in place. That's something we're struggling. And I think in our institute, we're very lucky because they are pushing towards that, and that's why they built the data science team. Outsourcing will also be challenging, especially now with GDPR. It's not going to be easy to hire somebody to look at patient data, and so that's also. So my thoughts here is that probably hospitals have to really start building their teams from within, not outsourcing. Also, how can we involve more of the domain experts in the conversation, avoiding the language of you're going to be replaced in 5 years by an algorithm. And also how, now on the other side, how can we attract more data savvy people in the hospitals? So this is also very important. So these two worlds can meet. Well, thank you for listening. There's a mic. Sure.
Sorry, I have a very specific question about the Lyme explainers that you had on the previous slide, if you want to go back to them for a sec. And I don't know that there's a right or wrong answer here, it's just I'm seeing a lot of observations here that I've empirically seen while using Lyme as well. And the first is that the values on the coefficients are often very close to 0. So I'm wondering how you have confidence that these are meaningful explanations as opposed to just noise, because this is something I've encountered as well. And then the other question I have is, I know empirically Lyme has been shown to be very unstable for very similar explanations. So do you ever come across a situation where you have like two scans that are very similar, but the explanations are dramatically different? And how do you deal with that?
I didn't have much time to get more into the details of that, but you're right. Lyme, we've noticed that it's not very stable, you're right. Sometimes we run even the same patient and it gives us a little bit different results. So there are some thoughts there. One thought is if you want to have some type of analysis on this, you can just run it 10 times, let's say, and you have like some then range of what was the variation of your feature importance. But at the first stage, we just wanted to have like a quick visual view, so we're not very picky yet about that aspect. But you're right, and there's another library that I want to try, SHAP, that I saw that some people are using, which, from what I understand, is linked with Lyme, but anyway, we're going to explore both cases. We don't really have a strong opinion on this yet.
Cool. Thank you.
Questions? Thanks, Patrick and Pavlos.
Thank you.
There's another question over there.
Thank you. Great talk. To what extent are there other teams around the world working on similar problems? Do you know about them? Are you able to coordinate with them? Are you able to share perhaps anonymized data? Because obviously this is a sort of field where the more data you have, the better in terms of extracting meaningful results.
Yes, sharing patient data is among different hospitals is still very difficult. From what we've seen in general, there's not really a way that has been a way that has been put in place. One thing I know that in the Netherlands they tried was to share the model. So that's another way that is being discussed, which might be safer. Yes, and then there are some initiatives that are more local initiatives to start building data science teams. So this, I think, is really, we're in the early phase of this. That's my feeling, but we are catching up.
And it's still in research phase. So we're trying to really work towards a clinical implementation, which will actually be used by a clinician. That's also, I think we're catching up now in what we're doing.
Looking at the questions you got here, a lot of the medical research in AI I've seen has been imaging focused, has been understanding scans. Are you aware of anybody doing research going into other areas like interpretation of blood test results or attempting to do much by the way of natural language understanding of the more free-form data sources?
Good question. No, I'm not really aware of it, but there's also, since we just started talking to clinicians, let's put it that way. So we also need to, let's say, explore the field, because we are in radiotherapy and it's sort of maybe limiting us. So we need to broaden our view as well. But I'm not aware of these applications, but I'm sure that they might be very useful, yes indeed.
But you're right, in natural language, for example, consultation is mostly text.
Yeah.
So it's the first step of this process. You would expect we're going to do that first. In some hospitals, they're not always also electronically, these consultations.
So you haven't yet had a chance to explore, looking at any part of the history to go to add to the scans, for example, to aid the interpretation at this stage.
Excuse me, to add?
So, to look at the clinical presentation and the symptoms that people are going, as well as the scans to enhance that data set. It's not something you had a chance to look at yet.
To enhance data set, like data augmentation, you mean on the images?
No, just using data other than the images to say how was the patient feeling, or other things to go with that.
Well, no, we haven't. No. But
yeah. Yeah, these are very good, valid points. They sort of feel like obvious first steps, but what you're describing also about outcome and toxicity, like a patient having an app saying that I started feeling not, like giving us some metrics of how he feels from there are not many places in the world that they keep track of the patient, but that's again doctor by doctor, and this is a nice area of that we should evolve that way.
Hi, very good talk. You told about the challenge of having missing sort of data savvy people in the clinical world. What about trying to bridge the gap from the other side, so sort of having clinical savvy data people? Is that possible?
We are the clinical data savvy people.
Good question.
Well, I mean, it's a good question. A clinical data, that's the best thing, right? You have the doctor that writes Python, but that does not exist easily, right? Because because they go through a very, very different training, and they have to learn a lot of things, and they have also a job. Like nobody's going to quit their job as a doctor to become a data scientist. So it's difficult. It's not as easy as in other fields that we see.
But it would be a very nice idea.
But there are some doctors that write Python.
Your background is physics, and most of the people in data science will have physics engineering background. Do we not need new ideas to do with medicine, where what I feel like affects the clinical outcomes, what my feelings are, what my biochemistry is related to your question? humans are not biological dynamical systems. Physics is very simple.
Yeah,
It's a simple dynamical system.
yeah.
But biology is more do you think we need new ideas? And does somebody have any ideas to deal with the complexity?
You take that.
A more holistic approach is what you
Yeah,
mean.
it's a complex system.
Yes,
very complex.
but we are very simple thinkers, so we need to. Yes, I think you're absolutely right, and I'm not sure if there's any. It's very compartmentalized, medical healthcare still. Yeah. I don't know. It would be a valid approach, but you need to start somewhere, and we started here, but things should get bigger and more inclusive. Yes, indeed.
What is the right kind of institutional context for doing medical data science? Because I'm struck that the brilliant work that you have done will improve outcomes perhaps at your hospital in the Netherlands. What about all the other hospitals in the Netherlands? What about the hospitals in France or the hospitals in Canada? Because I'm struck by the fact that when a pharmaceutical company develops a new drug, it is potentially can be licensed throughout the world. Similarly for a medical device, but yet because of the way your system is deployed, it doesn't seem to have the same global reach where there is a global need.
Well,
Yes, please.
I don't agree. The global reach starts with the talk in PyData to begin with, and then you give incentive to people to get in there. And then this other question is that, I mean, it's a valid point what you're saying, it's true. It's just that we're trying to change this and show a paradigm from within a hospital. With the pharmaceutical license, you said one solution, some hospitals, the biggest hospitals, in order to avoid being so much charged about pharmaceutical that have brands, was they build their own pharmacies. So that's how we should do with data science. I think hospitals should build their own data science teams, and then they talk to each other, they have meetings, and they grow, maybe.
Yeah, thank you for the talk. It's very interesting. I think I can really appreciate the difficulty that you have. That's almost, you've got 101 problems that stop you from really having the effect that I think some of the people have hinted at. I'm thinking of the NHS digital equivalent in the UK, where actually a lot of what's stopping you at the moment is not really anything that you can do in your remit, in your in the situation you're in, but it's almost, how much the local government can help you expand this out. I'm just wondering, to what point do you think that you're soon going to reach a blocker where there's only so far you can go before you've got buy-in from the government to really expand the remit of where you can go with this?
So you mean the local governments should decide to fund, since it's sort of public sector system, the healthcare?
Yeah, so I guess there's always more hospitals that you can run these trials on, there's always more that you can try and test, and there's always more implements that you can run for. So do you need that now? Do you need that, if you've got a lot more room to go for in the area that you've got right now? I'm just wondering, where does it become a government, like a regional government problem, more than the problem that you're working on right now?
Yeah.
Well, I mean, I hope that the governments, and they do see that, like there's a lot of talking about data science. So the hope is that there will be, I think, the end goal would be you have specialized people working in data science problems in the hospital, or they manage to do something with this data protection rule, so they outsource, so you have some sort of collaboration of the government to companies. I'm not sure if that's going to happen easily. But the hope is that the governments will start seeing the need for this. But we're trying to prove an example of something that would be...
Yeah, exactly. Yeah, so I was referring to you guys as almost a POC, which is that the government see this, they see the concept, they see the value of it. And I'm wondering what the feedback you've got from governments to, have they recognised that this is a good POC that they want to expand this out to?
Yeah, maybe we should approach the government.
Yeah, we should.
Yeah, these are good questions. We don't really have good answers.
We haven't done too much strategic thinking. That's yet, maybe. Valid point. Yeah.
Thanks for your questions. Please bring others offline. Thanks.
I think you had a question,
speakers.
right? Oh, that's okay.
We are running out of time.
Okay.
Sorry. Thanks.